All right, so the waiting time, this is a problem 40. The waiting times for a new roller coaster ride are normally distributed with a mean of 35 and a standard deviation of 10. If there are 150,000 riders in the first summer, which of the following is the shortest time interval associated with 100,000 riders? So I want to figure out, based on if there's 150, I want the interval to contain 100 of them. One thing to keep in mind here is that if I want the shortest interval, I'm going to be centered about the mean. The shortest interval will always be centered about the mean, but I have to make sure that I have at least 100,000 riders. So 2/3 of the riders need to be there. Quite frankly, just using what I know about the empirical rule, 100 over 150, that's 2/3, which is 67%, or 0.667, which is pretty close to 68% of plus or minus 1. So if I were just guessing with this, I'm going to guess it's going to be pretty close to plus or minus 1, which is, if this is 10 minutes and my mean's 35, I'm guessing it's going to be pretty close to somewhere between 25 and 45 minutes. So without even doing any computations, I'm going to guess if that's my answer. So this is a plug and chug. And if you're not sure which one, you can always check each one of them. You can do a norm CDF for each one of them. And so second bar is normal CDF. And if I didn't have that clue, I could have gone 0, 31.7, mean of 35, standard deviation of 10. I get 0.37 times 150. 1, 2, 3. It's like, oh, that's not the right amount. Second bars, norm CDF, and I keep doing that. I go 31.7 to 39.3 times 150. That still doesn't get me to the 100. It's not that close. I go to the next one, which is the one my best guess was going to be, 25.3 to 44.7. I multiply that times the 150, pretty close to the 100. I'm sure that that's my answer. All right, this is problem number 42. Company 1 manufactures bomb fuses that burn an average of 50 minutes with a standard deviation of 10 minutes, while Company 2 advertises a burn of 55 with a standard deviation of 5. Which company is more likely to last at least 1 hour? All right, so let's do this. All we really have to do, we can do probabilities, but we can also cut in and just do these as z-scores on this one. We can do either one. So we have company one. Company 1 has a mean of 50 and a standard deviation of 10. Company 2, 55, standard deviation of 5. This one needs to be 60 minutes. This needs to be 60 minutes. So if I go z equals x minus mu over sigma, so this is going to be 60 minus 50 over 10. That's 1 standard deviation, so z equals 1. If I do the same thing over here, z equals x minus mu over sigma equals 55 minus 5 over 5. So z also equals 1. Because they have the same z-score, I know they have the same probabilities. I am going to check that out just real quickly so I can show you. Second bar is normal CDF, 60. Upper bound is infinity. Mean was 50, standard deviation is 10. 0.1586 for company 1. For company 2, second var's norm CDF. Lower is now 60, upper is infinity, means 55, standard deviation is 5. And I also get 0.1586. So both companies, the fuse will at least last 1 hour is 15.9. All right. The time for the first stage of an assembly line is normally distributed with a mean of 28 minutes and a variance of 5, while the time required for an independent stage is normally distributed with a mean of 17 and a variance of 4. What's the probability that the two stages take more than 50 minutes? So we're adding two stages together. Well, we can add means directly. So adding means directly is 28 and 17. U of 1 plus 2 is 28 plus 17 is 45. But we can't add standard deviations directly. We have to square them first. And so we have a variance and a variance, and so they're already squared, which was nice of them. So we have variance is going to be, or the standard deviation is going to be the square root of 5 plus 4. Now I can add these directly because it called these variances. So they're not standard deviations, they're variances. So 5 plus 4 is 9, so my standard deviation is 3. Now we want the probability that the two stages take more than 50 minutes. Well, I expect it to take 45. That's the mean or the combined amount of time. We want to know the likelihood that it's greater than 50. And so that's what we're looking for. So the probability that Z is greater than 50 minus 45 over 3. My lower bound is 50, so we're going to go second bars, normal, CDF, lower bound 50, upper bound infinity, mean is 45, standard deviation is 3, and 0.0477, or about 0.0477. So this answer would be A. The yearly rainfall along the coast of Liberia is 210 inches. What is the standard deviation if 20% of the years have rainfalls under 200 inches? So we have a mean of 210. We want to know what it is if this is 200. Well, we know that this area is 0.20. So Z equals X minus mu over sigma. I don't know my standard deviation, but I have 200 minus 210. We're looking for standard deviation. Then I can do an inverse norm of 0.2. When I do that, second bars, inverse norm, 0.2, mean is 0, standard deviation 1. I get negative 0.8416. When I do my algebra, I end up with negative 10 divided by the negative 0.8416, and I get 11.88 inches. All right. You can also check it out just by running the inverse norm, which would be 0.2 mean of 210. Oh, you can't. You couldn't have done it. Sorry, you had to use algebra on this one. I had to do complicated math. All right, but whenever you do an inverse norm, you always have to provide the z-score. You always need to provide the z-score. That's a good question. Looking at number 44, suppose fastball speeds in collegiate baseball are normally distributed with a mean of 86 and a standard deviation of 4. Suppose further that Major League Scouts will only consider pitchers who can throw at least 90. What's the percentage of prospects who can throw speeds over 95? So once again, this is they only consider if you can throw 90, and that's not what we're starting out with. We're starting off with this. We have a mean of 86. So this is a given situation, given that they throw over 90, what's the probability they throw over 95? So we need to figure out this part first. So we need the probability that Z is greater than 90 minus 86 over 4. $90, infinity, 86, 4, 0.1586. And then the intersection part is the 95 plus. So in this case, the probability that Z is greater than 95 minus 86 over 4. .0122. And since it was considered, that's like saying given. So given's in the denominator and the intersection's on top. So 0.0122 divided by 0.1586. So B, 7.7%. So really, even though there's not a big difference in speed between 90 and 95, only 7 or almost 8% of those who can throw 90 can throw 95. Okay, so this is problem 55, which is an inverse norm problem, and actually a fairly challenging one, but certainly one that I would consider fair. So a soft drink dispenser can be adjusted to deliver any fixed number of ounces. If the machine is operating with standard deviation of 0.3, what would be the mean setting so that a 12-ounce cup will overflow less than 1% of the time? So the mean's here. We don't know what it is. All right, so the mean's in the center. We don't know what it is. This is what we're looking for. And up here is 12 ounces. And I have 0.01 shaded up here. And here's why. This 12 ounces, I have to have less than 12 ounces in the cup. If I put more than 12 ounces, it overflows. Well, it overflows how much of the time? 1% of the time. And 99% of the time, which is this area down here, it won't overflow. So basically the machine's going to set up so that 99% of the time it doesn't overflow, 1% of the time it does. So Z equals X minus mu over sigma, because it's a normal. I start plugging in everything I know. Well, what I do know is I know my standard deviation is 0.3. I don't know my mean, but I know that I can't put more than 12 ounces in the cup. So if I make the mistake, which would be very easy to do, go second vars, inverse norm, I get 0.01, mean is 0, standard deviation of 1, and I get a negative Z-score. But since I'm above the mean, I shouldn't have a negative Z-score. This should be a positive Z-score. I should have run the 99%. So second vars, inverse norm, 0.99, and I get 2.326. All right, so 2.326 solved by algebra. And by the way, if you're not careful, you'll freak out, but don't work it out all the way, times 0.3 to subtract the 12. And I end up with a negative 11.3. And I know you're kind of nervous, but notice you also have a negative mean. Divide both sides by -1, and we end up with 11.3 equaling our mean, and that's our answer. All right? Now remember, our 12 ounces had to be above our mean, and anything above 12 would be overflow. All right, I was asked to do number 57. 57 makes me happy because it's a more straightforward distribution of means. All right. So suppose the average outstanding loan balance for college graduates is 23,500 with a standard deviation of 7,200. In a simple random sample of 50, what's the probability that their mean is under 21,000? So we have this at 23,500. This is 21,000. And notice they said this is a mean. So this is an X bar. So that means I need to be working with Z equals X bar minus mu sigma divided by the root of N. So the probability that Z is less than 21,000 minus a mean of 23,500, standard deviation 7,200 divided by the root of 50. So the second vars, normal, CDF, negative infinity, upper bound is 21,000. That's the way I shaded it. 23,500 is my mean. Standard deviation 7,200 divided by 50 caret 0.5. And I end up getting 0.0070. Going back to number 57, it says, the question was asked, hey, this formula applies whether or not it's normal or not, because they didn't tell us it was normal. It could have been skewed, probably is actually skewed, all right? But our sample size was 50. So since we're working with the distribution, of the means, and our sample size is 50, so n is greater than or equal to 30, and we're working with the distribution of the means, then we can use the Z equals X minus mu, X bar minus mu sigma divided by square root of n. We can use this formula because our sample size of 50, when we're talking about the distribution of means, is greater than 30. In this particular case, if n is less than 30, I couldn't use it because they didn't tell me if the underlying population is normal. If the underlying population is normal, I can use this all the time. Okay? If the underlying population is normal and we're talking about means, I can use it all the time. But since they didn't tell me, had my sample been 25, I would have been stuck and I wouldn't have been able to work that problem. By the way, these are added questions that come in the chat, so you owe your friends for being here.